the Big Bang Theory has lost some validity with the new information discovered by the James Webb Space Telescope. We just made a surprising discovery that is revolutionizing world physics. The recent image captured by this telescope has generated compelling arguments that have surprised experts, putting an end to much speculation. The telescope's most recent discovery is visually stunning and could transform our understanding of the universe. The discussion among experts that this image has resolved centers on the perception of the cosmos. The stunning image taken by the James Webb Space Telescope challenges our understanding of the universe. This finding addresses one of the main problems in astrophysics, the age of the universe and its rate of expansion. Scientists from different generations have been puzzled by this unsolved phenomenon and have carried out numerous studies in search of answers. Cosmologists investigate how the universe originated, how it works, how it has changed over time, and how it might end. In the last 100 years, great advances have been made in this field. The Big Bang Theory, the most widely accepted theory in cosmology, holds that the universe has been expanding for approximately 13.8 billion years, starting from an extremely hot and dense state. The Hubble constant, which indicates the expansion rate of the universe, is used to measure this growth. However, determining how to measure the Hubble constant is not straightforward, and there are two main methods: local measurements and measurements of the early universe in space. Projects such as stars and Type Ia supernovae, which are used as standard candles because of their consistent brightness, allow astronomers to measure how far away they are and thus calculate the Hubble constant. As the universe expands at varying speeds over time, scientists can calculate the Hubble constant. Accordingly, there are two main approaches. One is the measurement of the early universe. Scientists use readings of the cosmic microwave background radiation (CMB) discovered in the 1960s as the afterglow of the Big Bang. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its expansion rate by measuring the tiny ripples in temperature and polarization emitted by the CMB. However, there is a problem. These methods do not yield the same result. Local measurements suggest that the universe is expanding faster than the CMB data indicates. Scientists have been working hard to understand why the results differ. To unravel more mysteries of the universe further, studies are underway. The differences in measurement indicate that we do not yet understand all the signals or that there are errors in one or both methodologies. But thanks to the James Webb Space Telescope, we can peer farther into the darkness of space than ever before, revealing elements, planets, and galaxies we never thought possible. Scientists hoped the data would help them calculate the Hubble constant, but first wave of data has revealed unexpected findings that don't align with existing expectations. Could this information give us a new perspective on space? We may need to rethink what we know about how the universe works. We might discover particles and forces never seen before, or we may find that dark energy, the unknown force accelerating the expansion of the universe, needs to be reconsidered. With each new discovery our ideas about space evolve. For example, the cosmic microwave background radiation, discovered in 1965, was strong proof of the Big Bang Theory. Before that, scientists believed the universe would last forever, expanding at a constant rate indefinitely. However, new evidence showed this was not the case. In the late 1990s, when it was discovered that the universe was accelerating in its expansion, scientists also learned about dark energy and its impact. Every time we discover something new, we test whether it fits with previous knowledge and develop new ways of understanding the universe. Without this process, the challenges we face in cosmology could not lead us to better insights. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Scientists around the world are interested in this cosmological puzzle because everyone wants to know more about the universe. Most importantly, it demonstrates how science is always evolving as we learn more about space. Structure-age tension is another concept that goes hand in hand with Hubble tension and refers to how matter is distributed in space. We use this information to model the structure of the universe and observe how it has changed over time. Some areas of space have many galaxies clustered together while others are relatively empty. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to look at how different densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see the effects of dark matter, which does not emit light and is therefore undetectable. Scientists also analyze cosmic microwave background, the CMB radiation, the afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information from the early universe. By studying the CMBB, scientists can understand how the universe was full of irregularities when formed. However, this data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than what is observed through gravitational lensing. This implies that something fundamental is missing in our interpretation, bringing us back to the mystery of dark matter and how it operates. According to Rice, he and his team were able to redefine their work thanks to the Webb Space Telescope and wanted to investigate whether a possible error in the Hubble Space Telescope's measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe, Rice said in an interview with an astronomical magazine in the United States. Using the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and study cosmic distances with ever more precision. Both dark matter and dark energy are enigmatic components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the leading explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy might influence these cosmic phenomena. Let me know your opinion in the comments box. If you like the video, remember to like and subscribe. Thank you so much for watching, and I'll see you in the next one. Thank you. As scientists continue to analyze data from the James Webb Space Telescope, the foundations of modern cosmology are facing unprecedented scrutiny. The telescope's ability to observe distant galaxies from just a few 100 million years after the Big Bang has challenged existing models of galaxy formation. Contrary to prior assumptions, the early universe appears to have hosted more mature, massive galaxies than expected. These findings suggest that either galaxy formation occurred much faster than previously believed, or our understanding of the physics governing the early universe needs a fundamental revision. 1. Emerging theory to explain these discrepancies involves modifications to the lambda CDM model, the current standard model of cosmology, which includes cold dark matter CDM and a cosmological constant lambda, representing dark energy. Some physicists propose that dark energy may not be constant at all, but instead may change over time or interact with dark matter in unknown ways. This dynamic form of dark energy, sometimes referred to as quintessence, could potentially account for variations in cosmic expansion rates observed at different epochs. Other researchers are exploring alternative models of gravity, such as modified Newtonian dynamics, manned or scalar tensor theories, which propose changes to Einstein's general theory of relativity at cosmological scales. These theories attempt to explain phenomena like gravitational lensing and the formation of cosmic structure without invoking unknown entities like dark matter or dark energy. While controversial and not yet widely accepted, these ideas highlight the growing willingness of scientists to question long-held assumptions in light of new observational data. The JWST has also opened up opportunities to examine chemical composition and atmospheres of exoplanets, some of which orbit in the habitable zones of their stars. These studies may not directly impact our understanding of cosmological expansion, but they add valuable context about the evolution of matter, star systems, and the potential for life in the universe. Chemical fingerprints JWST detects in these atmospheres can also provide clues about the broader distribution of elements in the universe, another important piece of the cosmological puzzle.